Welcome to a special Lightning Talks event hosted by Boise State University in support of the NSF Upwards collaboration. An opportunity born of the CHIPS and Science Act, Upwards is a collaboration between 6 United States universities and 5 Japanese universities, working with industry partners Micron and Tokyo Electron Limited to provide advanced training and research opportunities for students, faculty, and professionals. This collaboration addresses the demand for a highly trained microelectronics and semiconductor workforce that builds global and domestic capacity in the semiconductor field. Thank you for everyone for attending today's event, and a special thank you to our presenters. We're excited to hear from each of you and to learn a little something new about today's topic, materials and devices for memory. Before we hear from our speakers, I would first like to introduce Dr. Daniel Lamborn, Executive Director of the Institute for Microelectronics Education and Research at Boise State University, for some opening remarks. Dr. Daniel Lamborn earned his Bachelor's of Science in Chemical Engineering from the University of Utah before going on to earn his PhD in Chemical Engineering from Pennsylvania State University, where his research was focused on superconducting thin film deposition and process modeling. From there, Dan started a 16-year career at Intel, where he held roles such as process development, pathfinding, and engineering, equipment design and installation, and supply chain management. Dan has since returned to Idaho to serve as the executive director for the Murr Institute. Dan, the floor is yours.
Thank you very much, Catherine. Can everyone hear me okay? I think that is a yes. Thanks. I'm really excited to be here. I'm really excited to be able to represent Boise State and be able to join you all here. It's an honor to be with all of you at this time. Upwards is a really interesting program where we get to have some really interesting engagements with a number of outstanding institutions. I really look forward to being able to learn as much as we can from all of you and to be able to collaborate on many topics moving forward. Please reach out to us at any point in time for any input or assistance that Boise State might be able to provide you. Really looking forward, and again, thank you very much, and we're really looking forward to being able to work and collaborate with you all.
Awesome. Thank you so much, Dan. Next, I would like to introduce our representative from Micron, Janine Rush-Byers. Janine Rush-Byers has been with Micron and the Micron Foundation since 2006. As a director of strategic university partnerships, Janine works with domestic and international universities to build strategic, long-term partnerships focusing on engineering programs, students, and faculty members. She is a board member of the Engineering Plus Advisory Board at Boise State University, the LSAMP program at University of Washington, the Idaho Global Entrepreneurial Mission, the Treasure Valley Economic Partnership, and the Children's Museum of Idaho. She holds a bachelor's degree in engineering from the University of Washington and an MBA from Boise State University. Janine, go ahead.
Great. Thank you, everybody. This is such an exciting day for me as the Upwards program is really starting to come to fruition. This multi-university network between the US and Japan is really focused on building awareness of the industry and creating opportunities for students and faculty, really with a priority and focus for our women. The Upwards program has 5 main pillars: women in semiconductors, curriculum design and implementation, experiential learning, student and faculty exchanges, and semiconductor and memory-centric research, which is why we're here today. So I welcome everybody and thank you for creating this exciting environment and bringing more opportunities and more awareness to the exciting world of semiconductor research, much of which has been somewhat invisible to many of students over the past 25 years. So welcome everybody and thank you again.
Thank you so much, Janine, for being here and for speaking. Appreciate it. Now we will go ahead and transition to the lightning talks. So for our lightning talks, we have 5 speakers who will each have 5 minutes to present on their topic. We're going to hold questions and discussions until the end of all the presentations, at which point the audience members will have a chance to talk with presenters in breakout rooms. And I'll go a little more into the breakout rooms and that process when we get there. But first, I would like to present our first speaker, Dr. Long Lee. Dr. Long Lee's general research interest is in the development of AI and machine learning-driven multi-scale modeling techniques to accelerate material design, including processing, structures, properties, and performance. She closely works with experimentalists and data scientists to optimize her computational models and guide experiments. Dr. Lee teaches electrical properties of material survey of material science, computational material sciences, solid state thermodynamics, phase transformations, and kinetics at Boise State University. Her general education interests is the development of online learning models in computational modeling and AI machine learning for students, researchers, and engineers who are interested in the techniques but have no modeling or program experience. She's going to talk to us today about the development of AI and machine learning assisted multi-scale modeling techniques for semiconductor and memory research. Dr. Lee, the floor is yours.
Thank you. Thanks for the introductions. And yeah, I am from the Boise State, and I have a material theory and modeling groups. And my group's focus is on developing AI machine learning assisted multi-scale modeling techniques and to accelerate the material design, including processing, structure, property, and performance. And as you can see in the left figure, and we combine ab initio, so starting from the very beginning, the smallest length scale, ab initio quantum mechanics modeling, and classical molecular dynamics, and microstructure modeling, and finite element modeling. And we also try to introduce AI and machine learning techniques and on different steps and of the modeling. Where do we use those the techniques? And on the right, I list the three major semiconductor related projects and my group have worked on or are working on. The first one is to model the atomic layer deposition processes. And we collaborated with Professor Elton Granias at Boise State to study the chemical reaction between the precursor and the various substrates. And our models can help identify the controlling factor and during the thin film growth. And so we all know this, people use atomic layer deposition like to growth, probably, for example, two-dimensional transition metal like chalcogenide thin film or metal oxide for the memory device. And the second project and we work on is predict the property and performance of the transition metal like chalcogenide thin film and metal oxide. And you see in the middle figures and which is the transport properties and actually is predicted by our in-house code. So besides the structure and electronic property, our models can predict like, for example, the thermal transport property between the interfaces, and we also study the different metal oxide and for memory devices. And so you can see a small table and next to that the figures. And the third project and we work on is to model the plasma etching and for advanced dynamics of random access memory and the flash memory technologies. And we build up the model and for the application and mechanism of the anisotropic two-step silicon nitride etching and with the hydrogen, the plasma conditioning. So it will be able to have a detailed understanding and what really going on and during the etching process and through our models. So at the end, and definitely I'm very glad to collaborate, and we would love to collaborate with more computational modelers and data scientists and to strengthen our AI machine learning assisted multi-scaled models and for the semiconductor and memory material and device research. And we can target like processing structure, property, performance, and from the small scale up to the larger scales. And we also love to collaborate with the experimental groups, and we hope that our model could provide more details and to help understand the experimental measurement and also the process, and also can guide the experiments. And the last I want to mention is like Boise State is going to host a 2-week virtual summer short course and this summer. And this summer short course will focus on computational modeling and AI machine learning technique and for semiconductors. And our target and audience will be student, faculty, researcher, and the staff, and at all upwards partner university, Micron and TEL in the US and Japan. And so we don't require any programming background. So we targeting someone who's interested in using those techniques and for their research. Thank you.
Thank you so much, Dr. Lee. We appreciate you coming and telling us all about your program and your research interests. So we'll go ahead and move on to our next speaker, Dr. Kenji Ishikawa. Dr. Kenji Ishikawa is a professor of Center for Low Temperature Plasma Science of Nagoya University. He holds a PhD of engineering and joined Nagoya University in 2009. His scientific research interests involve plasma surface interactions in semiconductor processes and cover plasma effects on liquids and living organisms, involving plasma medicine and plasma agriculture studies. He has 324 publications with over 4,445 citations and has been invited to speak at more than 70 scientific meetings. So we'll go ahead and move on to our next speaker, Dr. Ravishankar Sundararaman. Dr. Ravishankar Sundararaman is an associate professor of material science and engineering, and Priti and Mukesh Chatter, of 82 Career Development Chair at Rensselaer Polytechnic University. He received a PhD in physics from Cornell University in 2013 and was a postdoctoral fellow of the Joint Center for Artificial Photosynthesis at Caltech till 2016. His research group pushes the limits of first principles materials design for energy and nanoelectronic applications by combining quantum mechanical and classical simulations. He also leads the development of open source software for such ab initio multi-physics calculations on diverse high-performance computing environments. I hope I'm saying this all right. He is the recipient of the AIME Robert Lansing Hardy Award in 2020 and the Rensselaer School of Engineering Research Excellent Award in 2020. He will be speaking to us today on discovering materials to efficiently connect nanoscale transistors to, in future chips. The floor is yours.
All right, so I'm going to talk about one specific research area that we've been leading for the last few years. This is mostly supported by the Semiconductor Research Corporation. So with transistors and semiconductor chips shrinking down further, the metal wires connecting them into computing circuits, as shown in the top left panel, also need to get smaller. This increases the resistance of the wires substantially, and the RC, resistance capacitance delay in these nanoscale interconnects, is increasingly becoming the key performance bottleneck. Now, the reason for the higher resistance is twofold. It's not just that the cross-section areas of the wires is getting smaller, which is of course happening, but in addition to that, the resistivity of the metals is also increasing as you reduce the dimension, which is what is shown in the top center panel. This resistivity increase happens because the electrons in the metal now frequently scatter against the surfaces of the wire, in addition to the vibrations and imperfections within the volume of the metal, which leads to a 1 over dimension kind of resistivity increase. Now, note that copper, which is well known as the best conductor at macroscopic dimensions, is no longer the best conductor at nanoscale. So this points to a materials design opportunity. We could find materials that end up becoming better conductors at the nanoscale, even if they are not the best conductor at macroscopic dimensions. So one strategy we've been working on towards this is shown on the right-hand side. So if you think about copper, it's an isotropic metal, which means that the electrons in it are equally likely to be in almost any direction. So with that equal probability distribution, on average, the electrons are going to encounter the surface, scatter, lose their momentum, contribute to resistivity at some rate. But what if you could design an anisotropic metal where the velocities of the electrons are channeled primarily along the direction that you want to transport the current? Then the electrons would encounter the surface less frequently, and hence they should be less sensitive to the surface, and the resistivity should increase less as you're reducing the wire dimensions down. So as shown on the bottom, this is effectively like putting blinders on the electrons. It's keeping them from getting distracted by the surfaces, and hence not getting scattered and contributing to a resistivity increase. So with this strategy identified, we conducted electronic structure calculations of thousands of materials. And for each of them, we calculated these Fermi surface shapes as shown in the bottom center, which tells you what are the directions of electron velocities possible. In particular, the electron velocities are perpendicular to the surfaces shown here. So particularly useful for wires are the Fermi surfaces shown for cobalt tin and yttrium cobalt boride, which we predicted as two of the most promising candidates. They have multiple sheets of Fermi surface next to each other, which means there are a large number of electron velocities all pointing in the same direction. So if you make a wire pointed along that direction, then those electrons are primarily going to go without much nanoscale sensitivity as you go down to the nanoscale. So putting that all together, we were able to do detailed quantum mechanical simulations of what we expect if you make nanoscale wires out of these materials. And that's shown in the final plot on the bottom left. And we find that these candidates, cobalt tin and yttrium cobalt boride in particular, are expected to achieve a 2 to 5x improvement compared to copper at nanoscale dimensions. And tests of these materials are currently underway from our experimental collaborators at RPI, Cornell, and Notre Dame as a part of various SRC jump centers. Thank you.
Thank you so much, Dr. Sundararaman. We appreciate you coming in and talking about your research. We'll go ahead and move on to our next speaker, Ms. Chihiro Watanabe. Ms. Chihiro Watanabe received her Bachelor's of Science degree from Hiroshima University's School of Engineering in 2022 and will earn her Master's of Science degree from the Graduate School of Advanced Science and Engineering from Hiroshima University in March of 2024. She will then be entering Hiroshima University's doctoral course of Graduate School of Advanced Science and Engineering in April of 2024. She is currently working on reliability of magnetic tunnel junction, such as MTJ fabrication process to suppress leakage current, switching characteristics, time-dependent dielectric breakdown, and evaluation of intermediate states. She's going to talk to us today about isolation method of magnetic tunnel junction using SIN sidewall and characteristics. Ms. Watanabe, the floor is yours.
Thank you for introduction. Today, I will talk about isolation method of magnetic tunnel junction using SIN sidewall and characteristics. MRAM is emerging non-volatile memory and candidate of substitute for SRAM and DRAM. For MRAM, data is stored in magnetic tunnel junction. The basic structure of an MTJ consists of two ferromagnetic layers separated by a tunnel barrier. The magnetization direction of one ferromagnetic layer, free layer, can be changed, but that of the other ferromagnetic layer, pin layer, is fixed. Pin layer is fixed by the surf layer. It acts like a permanent magnet. When the magnetization direction of the free layer and pin layer are parallel, the resistance is low. And when they are anti-parallel, the resistance is high. In the MTJ, leakage current is a problem in the MRAM fabrication process because the etched metal deposits on the MGO side during device separation. Usually, all layers from the free layer to the pin layer are etched at once using ion beam etching. In this process, the angle of the IBE is adjusted to remove adhere materials. However, it's difficult to etch our devices in this way because of their different sizes and pitches. Therefore, we considered a structure in which the etched metal does not adhere to the side of MTJ of MGO by using SI sidewall. This is the process flow. First, the free layer and MGO are etched by the IBE. Next, SI sidewall are deposited using PCVD. The SIN is also etched by IBE so that the SI sidewall remain on the side of MGO and top electrode. Then etch the pin layer with IBE. This is the schematic cross-section of MTJ. In IV characteristics, the red line shows the result of MTJ without SI sidewall, and the blue line shows the result of MTJ with SI sidewall. The MTJ without SI sidewall was initially broken down. The current of MTJ with SI sidewall increases at 1.1 volt and becomes almost the same as that of the MTJ without SI sidewall. In the MTJ without SI sidewall, the current flows through the side of MGO, but in the MTJ with SI sidewall, the current flows through the MGO and the MGO block at 1.1 volt. In RV characteristics, the resistance changed AP state to P state at this point, and the resistance changed P state to AP state at this point. The resistivity switching can be observed. This figure shows the result of resistance stability. The switching tests were conducted for 50 million cycles. Light voltages are 0.6 volt and minus 0.6 volt. Lead voltage is 0.02 volt. Path width is 50 microseconds. Furthermore, the variation of resistance in parallel state was anti-parallel state 0.75% and the parallel state was 0.83%. Resistance is very stable for switching cycles. From these results, leakage current at the edge can be suppressed by attaching SI sidewall to the size of MgO. Sidewall is very effective to protect MgO insulator during bottom electrode etching. Therefore, MTJs can be manufactured stable regardless of size, shape, or pitch by using SI sidewall. Thank you.
Thank you so much, Ms. Watanabe. That was wonderful. We'll go ahead and move on to our next speaker, Dr. Karthik Srinivasan. Dr. Karthik Srinivasan is an assistant professor in the Electrical and Computer Engineering Department at Boise State University. Previously, he was a postdoctoral associate at Cornell University, and he earned his Master's of Science and PhD from the University of Minnesota, Twin Cities. Dr. Srinivasan leads the Applied Magnetics and Photonics Laboratory, and his group's research explores novel magnetic and optical materials and their integration with nanoscale devices for photonic computing and terahertz communications. He's going to talk to us today about a beyond electron paradigm, photonic memory and processors. Dr. Srinivasan, take it away.
Thank you, Catherine. As Catherine mentioned, I'm fairly new at Boise State, so a lot of the work that I'm going to be showing today is my vision for what the future should look like. So the key question that I want to ask today is, why should we think of a computation and storage capabilities beyond electrons? Electron-based systems suffer from dissipative losses, and I think Dr. Sundararaman quite aptly put those in his description. And like he said, these only worsen with increasing transistor densities. Another pressing issue is the memory CPU bottleneck, or the so-called infamous von Neumann bottleneck. More and more energy is spent in moving data rather than computing with them. This is quite counterproductive to all the advances made in computing designs. Two problems need immediate solutions: the limitations of electron-based technologies and the ever-tightening bottleneck between the CPU and memory. The Applied Magnetics and Photonics lab at Boise State draws inspiration from the brain and the near dissipation-less flow of photons in integrated waveguides, or photonic highways. Our goal is to design an end-to-end in-memory photonic processor that leverages phase change materials and beyond charge state variables of photons to produce multi-bit operations. These are expected to produce significant improvements to the energy efficiency and data rates. The materials that make this happen are typically magneto-optical phase change materials and multiferroic materials. Both of these systems exhibit coupled magnetic and structural orders. That is, if you change the crystalline state of the material, it results in different spin configurations within the crystal structure. Now, the question is, how do these materials help in redesigning energy-efficient photonics? This requires an understanding of how data is stored, accessed, and processed in subsystems. The crystalline phase of the material is our fundamental unit of information. The binary categorizations will typically associate an amorphous state to a binary 0 and the crystalline state to a binary 1, or vice versa. But the ability to tune these material systems to exhibit several intermediary crystalline and amorphous states can lead to a multi-level information storage. Now the question is, why do I want to couple magnetics into these systems? Conventional light-matter interactions produce changes to transmittance. However, to effectively modulate both the polarization and phase of light, we need systems that can break both inversion and time reversal symmetry. Magnetic inclusions in a phase change material system can aid in simultaneous tuning of amplitude, phase, polarization of the interacting light. Integrating such materials with photonic waveguides requires several considerations. One such is the stimulus that induces a phase change. Our designs are aiming to provide these stimuli in two different ways. We can either do it through integrated nanotransducers that convert electrical pulses to thermal energy, which in turn induce phase change. Or we can also introduce a pump beam of light into the waveguide whose interaction with the cladding induces a localized phase change. And in either case, once the phase transformation has been achieved, a probe light can access the stored state of information. This would undergo amplitude, phase, polarization modification, thereby accurately capturing the information stored. Since different wavelengths of light do not interact with each other, these devices can also benefit from wavelength division multiplexing that further improves data carrying capacity. How does this mimic the brain? Waveguides and phase change materials are the synthetic equivalents of neurons and synapses. Since the plasticity of a synapse is a dynamic quantity that strongly depends on the past information transmitted through them, the ability to use guided light within a waveguide to change the phase of the material is the closest we can get to the role of factoring past signals and modulating present data streams. These innovations allow us to envision a future where traditional computing can be redefined and reconfigured with end-to-end integrated photonics that can achieve an energy budget of an attojoule per bit. Thank you.
Thank you so much, Dr. Srinivasan. I always love hearing about computing and like connections to the brain and how like they mirror back and forth. That's always very interesting to me. So thank you so much. All right. Well, I think we will go ahead and move on to our breakout room section. Thank you so much to all of our presenters. I really appreciate you guys being here and telling us all about your research and giving us some more insight on these amazing areas of research and memory and device machines.